The goals, some of them you've heard about. One of them was how particles acquire mass. And in fact, you've probably heard about the discovery of the Higgs boson, which was in 2012. And that was an extremely exciting discovery. It was really heartwarming to me that so many people were excited about this discovery, even though very few people actually understood what the Higgs boson was. But the Higgs boson is a particle that is associated with the mechanism by which elementary particles, particles like the electron or like quarks, acquire their mass. A secret is that they're not responsible for, it's not responsible for all the mass in the universe. Some of that comes about because of energy generated by the strong nuclear force, but it is responsible for the mass of a fundamental particle like the electron. So without that, the electron would just be a massless particle, and it wouldn't bind together in an atom. It would be, so it is essential to the features that we see. But the Large Hadron Collider was not designed solely to look for the Higgs boson. So the Higgs boson told us that this mechanism, called the Higgs mechanism, for how particles acquire their mass is correct. And it also gives a little bit of a clue to what created that mechanism. I don't have time to tell you all about it, but I do talk about it in the book. But we had some other puzzles that we were hoping would be answered too at the Large Hadron Collider. And those have to do with questions about why masses are what they are. Now, that might sound like a rather abstract question, but the fact is, if you use the tools that we as theoretical physicists have, namely quantum mechanics and special relativity, and combine them together, your guess, if you wrote down the equations to generate what you think the mass would be, your guess would be wrong, and it would be wrong by an enormous amount. It would be wrong by 17 orders of magnitude. Now, you might say, well, it's okay, you just guessed wrong. But the fact is, to get the right answer, you would require an enormous amount of tuning, or fine-tuning, or fudging, if you like, to get a cancellation of so many digits that you would get this small mass, even though you thought you should have this enormously bigger mass. And no one really thinks that's what's going on. Actually, these days, some physicists do. But it's really hard to imagine that things are adjusted that meticulously, that it would work. So that led physicists to think, what could be the reason that we got this prediction so wrong? Maybe there's more to physics than what we thought before. So we work with what's called the standard model. The standard model is the thing that describes those particles I told you about, like electrons and quarks and heavier partners and the forces through which they interact, and the Higgs boson. But it seems like that probably isn't the whole story. And it wouldn't be that surprising it's not the whole story, because, as I hope I've convinced you, every time we've looked at smaller distances, we've discovered new physics that underlies things that we would never have discovered unless we went to smaller distances. And in this case, it's a very mysterious problem why these masses are so small. And it's led to some very exotic ideas to solve it. One of those ideas is that there's actually a quantum mechanical version of symmetry called supersymmetry. That's something a lot of people thought might be the answer. Something I worked on with my collaborator Raman Sundram, and other people have worked on too, is that maybe the answer is actually connected to something as exotic as another dimension of space, a dimension beyond the ones we observe, beyond the three that we're familiar with, forward, backward, left, right, and up, down. Maybe there are, just like there are hidden particles, maybe there are actually hidden dimensions of space that we don't observe, and the answer lies hidden there. And the other thing people want to find at the Large Hadron Collider is something called dark matter, which is matter that has nothing to do with the standard model, yet the energy of the universe has 5 times as much of it as the ordinary matter. So there was a hope that we would find dark matter at the Large Hadron Collider. I would say that that hope is probably waning. There's a lot of reasons to think, I mean, after all, the Large Hadron Collider has been running. And it's been looking for all these things, but it found the Higgs boson, but not the other things. Which is why we think that it might require somewhat higher energy, even to go to even slightly smaller distances before we can really find out the answers to these questions. But as I said, one of the questions was answered in 2012. I already mentioned that that's associated with the Higgs boson, and I already told you a little bit what it's about. So I'm going to skip through this quickly. And I'm going to tell you that it has to do with the fact that there's something called a Higgs field. And in some sense, you can think of particles interacting with this Higgs field and thereby acquiring their mass. You might say it's really strange that mass isn't just there from the beginning. But if particles just fundamentally, if these elementary particles fundamentally had mass, the theory would give you nonsensical predictions. We knew that wasn't the case. So there had to be the mechanism, and this mechanism is known as the Higgs mechanism, named after Peter Higgs, one of the winners of the Nobel Prize. And I did write a book about that too. But where do we go from here? As I said, the Higgs boson isn't the final word. The Large Hadron Collider wasn't just designed for look for the Higgs, and we can even think about looking for extra dimensions. So I'm not going to tell you in detail, so I'm going to run through this very quickly, but I do want to give you a flavor for why we think an extra dimension of space could give us any insight at all. So again, the idea is that there's a dimension of space beyond what we see, beyond x, y, z, beyond left, right, forward, backward, up, down. And maybe some of these, in this extra dimension, we can understand connections that without including it, we wouldn't understand. And I confess, when I first started in physics, I probably would have thought this was as crazy an idea as maybe some of you think. But this problem of understanding why the Higgs mass is what it is a problem that's been around for decades. And no one has yet found a completely satisfactory solution. And there are reasons to think there might be extra dimensions having to do with something called string theory, a theory of quantum gravity, and having to do with the fact that we actually have no fundamental reason that there should be only 3 dimensions of space. So if there are connections that we can understand by including them, and as I'll explain, if these connections have experimental consequences that we can observe, it's well worth thinking about. So in fact, the idea is that an extra dimension can explain, sorry, let me just go back. An extra dimension can explain why the Higgs mass is so light, and essentially why gravity appears so weak, because the mass is so small. By the idea that gravity gets concentrated in a different location in the extra dimension. In some sense, we see only the tail end of gravity. If we look around us in 3-dimensional space, the space we know about, gravity looks the same everywhere. But we actually don't know that that would be true if there is another dimension of space. Now, if there is this other dimension of space, there is a very exciting observational consequence, which is that for particles that travel in extra dimensions, we would see partners we would see partners that are heavier. The heaviness would have to do with the fact that they have momentum in this other dimension. Because we don't see the other dimension, that momentum would seem to us like it's just a heavier particle. It would appear to us like there's a heavier particle traveling through. So if we think gravity travels in another dimension, we would expect to see heavier partners of the particle that communicates gravity, namely the graviton, in an extra dimension. And that's one of the things that the Large Hadron Collider looks for. So it looks for a collision of protons. Then it turns into what's called a Kaluza-Klein particle, named after the physicist and mathematician who first thought about this idea of having extra dimensions of space and what the consequences would be. But the exciting thing about our particular theory is that that particle would actually decay into particles we can observe. So rather than just leave the detector, leaving no trace, it can turn into things that we can actually observe, namely an electron, and it's what is called its antiparticle, a positron, like an electron, but with plus sign. So this Kaluza-Klein particle could turn into these particles, and that gives rise to an observational signature, something we can hope to see. Now I confess, when I first wrote this book, the Large Hadron Collider hadn't looked for it, and it has now, and it hasn't found it. And that could have 2 meanings. One is that this theory is just wrong, which is possible. And that's what we do as particle physicists. We think of possible theories, we think of the experimental consequences, and we test them. We hope we find the answer, but if we find out it's not the right answer, we move on and think about other things. That's okay too. We've learned more. But another possibility is that they're just a bit heavier. The Large Hadron Collider doesn't go up to super high energies. It went up to high enough energies to find the Higgs boson, but maybe we need to go to even a little bit higher energies. And that's the idea behind a collider proposed for China, and also what's called the FCC, the Future Circular Collider, which is proposed at CERN, which is where the current Large Hadron Collider resides. And so I'm very enthusiastic about the idea of probing yet higher energies. Even if I don't correctly predict what's there, I want to find out what's there so we know how to move on correctly. Science, too, has creative thinking, and it's often forgotten. People who don't do science think that it's very formulaic, you're just working out equations, you're kind of like just following the rules. But creative thinking, it turns out, is critical as much to good science as it is to art. Pushkin quote is that inspiration is needed in geometry just as much as in poetry. And to make real advances, you are creatively trying to tie together pieces and puzzles that we don't understand. So we're faced with this puzzle, for example, about particle masses, and we're trying to put it together to see what it can mean. And so you could just say, well, we know everything, but if you say that you know everything in advance, you're very likely to miss things. If you think maybe it's this, then you can say exactly what to look for, and then you can hope to find it. So art and science, I mean, it's just intrinsically human to go beyond the obvious. And there's always themes of exploration and discovery, and rich possibilities for how we understand. So I just want to mention a couple of things that I've done in the context of trying to combine together art and science. But I think it's a really great area that many people are exploring, and I think, and I congratulate CCCB on actually pursuing these connections a lot. So one thing I just want to mention is that we actually did an art project based on the idea of scale. And I worked with an artist, Leah Halloran, and we worked with the Los Angeles Art Association. We made an exhibit that was shown in several places. And the theme was art and scale. And what we did is we actually worked with artists, and we wanted projects that illustrated this idea of effective theory, where things look very different on big scales than they do on large scales. And we chose 7 artists who developed really interesting projects to do with that. And you see the difference between someone who can actually go out and explore and someone who's stuck here. And that's really how we always are when we explore these things in science. I mean, sometimes we can do experiments to probe specific ideas, but what we're trying to do is explore these regions that we don't directly get to access. We don't directly live in the world of an atom, or directly in the world of a nucleus, or directly in these subastomic structures. So when I wrote Knocking on Heaven's Door, I just want to emphasize that there were 2 different themes. One is creativity and discovery, just the elements that go into scientific thinking. Especially in America, people are very confused about what science is a lot of the time, and they say really nonsensical things about things being right and wrong. But I hope I've explained to you that it's not a simple right and wrong. It's a question of approximations and going beyond those approximations. So the role of scale, uncertainty, and risk play big roles, as do creativity and discovery. So one chapter was about creativity. It was actually called Truth and Beauty and Other Scientific Misconceptions. Because it's not a simple thing. The laws of physics aren't so beautiful sometimes, but we try to find ways to organize it that we understand what's going on. So I just want to close with a picture that I happened to come across at the Tate Museum, which shows that there are hidden riches and beauty in the universe. Here's a 2-dimensional world with a 3-dimensional picture. And the really nice thing is that it's a Chateau de Sion, which is right near CERN, which is where the Large Hadron Collider is. A lot of the time, you don't see things you're not looking for, which is the role of model builders. It's the role of us as physicists, trying to predict what might be there so that when we come across it, we don't just miss it.